Hi, Algebra 2 Honor students. Today we're going on to Unit 10, Day 5, and you can see our title here today is Infinite Geometric Series. Pretty cool topic. So if you've talked about sequences and maybe even a little bit of series in Algebra 1, this is really going to be a brand new concept for you. And thinking about a geometric series where we're adding up an infinite number of terms, that seems pretty tough to do, but we'll talk about some patterns that exist in infinite geometric series and how we can find the sum of an infinite geometric series. So let's start with a geometric series that we can find some sums within, and then maybe by the end, we'll be able to make some conclusions by analyzing this particular geometric series. So if we look at 16 plus 8 plus 4 plus ... hopefully you can see what the pattern is here as we're going from one term to the next. We're multiplying by a ratio of 1/2. So in this geometric series, we know that r equals 1/2. And remember that the formula for a geometric series is S sub n equals a1 times 1 minus r to the n over 1 minus r. So I want to be able to apply that geometric series formula for S sub 5, S sub 10, and S sub 100. Let's find the sum of the first 5 terms in this series, the sum of the first 10, the sum of the first 100. And we have enough info to do that. We know that A1 is 16. We know the ratio is 1/2. And we want to calculate this for these different values of n. So I'll encourage you to do this on your calculator real quick and see what you can come up with. And I'm just going to set it up where I say that A1 is 16, 1 minus 1/2 to the 5th in this first example over 1 minus 1/2. I'm just going to write the setups, and then I'll show you what the results are on my calculator as well. And we'll hopefully be able to make some conclusions about what's happening as we go out more and more terms in this list. So this would be just a new exponent of 10. And the last one, same thing with 100. Okay. If you have the setups like I have here, let's see what happens. I'll do my fancy fraction for you because I think that looks nice. Alpha y equals. All right, so I'm going to do 16 parentheses 1 minus 0.5 is probably easier to do than type in the 1/2 to the 5th power for the first one. And we're going to divide that by 1 minus 1/2 or 1 minus 0.5. Even though that's probably pretty tiny on your screen, you get the idea that the sum there of the first 5 terms is 31. All right, so let's write that down. So S sub 5 is 31. Moving on to S sub 10, we can be smart about this by either highlighting and hit enter so we can bring this down to the next line. The only thing that we're changing here is that exponent from 5 to 10, which is pretty convenient in a geometric series that you can find that sum for 10 terms by just changing that exponent. So we get 31.96875. So I want you to think about what happened. In S sub 5, we had 5 numbers in the list. We added them up and we got 31. Then I went on another 5 terms after that. So I added up 10 numbers in the list. And we got 31.96875, only a difference of less than 1 is what we added on. I mean, think about if the ratio is 1/2, what those other terms are that were being added on beyond S sub 5. And then think about as I go from the 10th number in the list to the 100th, those extra 90 terms. What's really being added on there? What's going to be that difference? Well, it sounds like you're going to get so much more of a sum when you go out to S sub 100, but let's confirm that when I type in 100 for that exponent, you actually just get 32 as an answer here. And if you type in 1,000, you'll be maybe surprised or not so surprised, I'm not sure. If I type in 1,000, that's going to say 32 as well. You're adding on another, from 100 to 1,000, another 900 terms, and you're still getting 32. So is it exactly 32? Maybe not quite. But it's the concept that in general, if I were to add up an infinite number of terms, notation S sub infinity, that in this example, it's getting really close to 32, isn't it, right? I mean, S sub 100 is 32, S sub 1,000 is 32. So yeah, as we go out forever and ever and ever, the sum is just always going to be 32. And because we're multiplying by this number 1/2, like we were saying earlier, it eventually will become such a small, tiny amount that we add on that in this example here, it's going to approach a specific value. So let's go back to what we know about our geometric series formula, S sub n. So we have A1 times 1 minus r to the n. The reason why this works out so nicely that we get an answer for S sub infinity is because that ratio is a specific type of number. So because the ratio in this example is 1/2, let's take a look at on the graph. You go to your calculator real quick. Let's look at what 1/2 to the x power looks like. And we haven't really studied exponentials together yet this year. That's, if I'm remembering correctly, actually unit 11. So it's not too far away. But if you hit zoom 6 for 1/2 to the x power, you'll notice that as x gets really, really large, that this is really quickly heading to 0. So the main idea here is as n goes to infinity, this part right here, the r to the n power, is getting closer and closer and closer to 0. So this is going to lead us towards developing a formula for an infinite geometric series. So instead of saying S sub n, where n is a specific number of terms that we're adding up, I'm going to write it as S sub infinity. And as n gets closer and closer to infinity, we saw on that graph that the function r to the n is getting closer and closer to 0. So as n goes to infinity, if this goes to 0, the numerator is just going to be a1 times 1 minus 0, or a1. And the denominator will be 1 minus r. This is the formula that we use for an infinite geometric series. Now, if I asked you to do the same thing for a different series, let's say we consider the series, let's do like 1 plus 2 plus 4 plus 8. Okay. Let's take a look at this series, which is a similar looking series to what I had at the top. This time we're doubling the terms, right? So if I said, what's the infinite sum here if I were to add up all of the terms, thinking of them infinitely? Well, let's approach it from the same perspective. Let's find S sub 5 first. So the first term in the list is 1. So the numerator is going to be 1 times, I don't really have to write that, 1 times 1 minus r to the n, so that's 2 to the 5th power if I want 5 terms, over 1 minus 2, and that turns out to be 31 here. Okay, so that's what we had before. So if I go out to 10 terms, will this be 32? Let's see. So if I change this exponent to finding the sum of the first 10 terms, wow, now we're at 1,023. Well, I don't know, maybe I just have to go out a little bit further. Let's go out like 20 terms, see if it starts approaching a specific value. So what did I say, 20 I was going to change this to? If I go out 20 terms, oh boy, we get to 1,048,575. So as compared to what I saw earlier with these sums getting really, really close to 32, it doesn't appear in this series that we're getting really, really close to anything in particular. So I'm going to give you a really fancy math word here. The infinite series here, S sub infinity, diverges. It's really approaching infinity. And the reason why is that these numbers are going to get larger and larger and larger. So since the numbers in the series are getting bigger, the infinite sum is just going to keep getting bigger and bigger and bigger and not approach a particular number. So what happens when it does approach a particular number like we saw in the beginning of the lesson? We say that the series converges. So the only thing you have to note about this particular series formula is that it converges only when what you're multiplying by, that ratio, is somewhere between 0 and 1. And I'm going to throw absolute value around that as well, because you can multiply by a negative ratio as long as it's between 0 and 1 and still have it such that you can find the infinite sum. So otherwise, if it's not a ratio between those bounds, we know that the series will diverge. So let's get some practice with this here. So if we look at some examples of some infinite geometric series. Let's take a look at the terms in the series. 27, 9, 3, 1, dot, dot, dot. Oops, that's supposed to be a 1, guys. There we go. Okay, can we find an infinite sum here, S sub infinity? Well, if I look at the common ratio, is that ratio that we're talking about something that's less than 1? And it turns out in this example that yes, we are multiplying by something less than 1. The ratio here is 1/3. So the nice thing about the infinite series formula is that it's pretty user-friendly. It's A1 over 1 minus R. So A1 in this example is 27. 1 minus the ratio, 1/3. That's what we're going to plug in here. So to clean this up, you can type it into the calculator. You can also really quickly get your answer by thinking of this as a complex fraction whose LCD is 3. And we love complex fractions from Unit 9, so we can do that. So we have 27 times 3 up top, which is 81. The bottom would be, if I distribute the 3, 3 minus 1, which is 2. So this series converges to the number 81 halves. Okay, if I were to type in really large values of n, we're going to get closer and closer and closer to 81 over 2. All right, let's try a few others for practice. So if I were to give you 8, 6, 4.5, dot, 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 as the terms in a geometric sequence, is this a geometric series that will converge for S sub infinity? Looks like it. I mean, when the terms are going down like that, that's typically good news. So A1 over 1 minus R would be 8 over, well, what is that common ratio here? It would be 6 over 8, which reduces to 3/4. And in fact, just to double check it, 4.5 over 6 also does reduce to 3/4. So you can check that out on the calculator. Okay, but we're going to plug in that ratio of 3/4 here. So to simplify, just like I did in the last one, maybe multiply the top and bottom by 4. So we get 32 up top, distribute the 4 on the bottom, 4 minus 3, which is 1. 32 over 1 is 32, just like one that we started with today that had an infinite sum of 32. Okay, so let's try something like 2, 6, 18, dot, dot, dot. Okay, so this is an infinite series with the first term of 2. And the ratio that I'm multiplying by here is I'm multiplying by 3 each time, right? So we get that the first term of 2 over -2 gives you an infinite series that converges to -1. Well, boy, that doesn't seem like it makes sense, does it? I'm adding 2 plus 6 plus 18 plus something. All right, 54 would be the next one technically. And I'm getting -1 as a sum if I add them up infinitely. Here's the little bit of a danger with infinite geometric series. You can always plug in the ratio in the first term and get an answer to pop out. But that answer only makes sense if the ratio is from 0 to 1. So this is not the correct answer. You cannot find the infinite sum because the ratio is 3. And since the ratio is bigger than 1, we would say that this series diverges. Okay, so you can actually stop before you even plug in anything for A1 and R. Sometimes students do that and they get an answer and they're like, okay, moving on. But you have to think in advance, will this converge or will it diverge? Let's bring in some summation notation. So you guys should be familiar with this. So the sum from k equals 1 to infinity. Why not? Of the terms 3/5 to the k in that series right there. So because of this exponential term, I'm looking at that base of 3/5 and knowing that that ratio is smaller than 1, this series will converge. So we know the ratio is 3/5. And in fact, when I plug in 1 for k, the first term is also 3/5. So given the ratio and given the value of A1, the infinite sum is 3/5 over 1 minus 3/5, which I can clean up by, let's see, LCD is 5 here, multiply the top and bottom by 5. So then the top is 3. The bottom is 5 minus 3, which is going to be 2. So the answer here is 3/2. And I just think it's so fascinating that, again, thinking about the series, adding up all those terms infinitely, we're approaching and we're converging to this value of 3/2 right here. Last thing we're gonna do for practice here is kind of applying this, and we'll do some more applications in class next time I see you, to writing a repeating decimal as a fraction. So here's what I'm gonna give you, 0.333333, forever and ever and ever. I'm guessing you might know what the fractional value of 0.3 repeating is. But in case you don't remember what 0.3 repeating is, how can I figure out what this repeating decimal is when written as a fraction, as a rational number? Well, I want you to think of this as being 0.3 plus 0.03. If you do 0.3 plus 0.03, that gets you 0.33, right? Plus 0.003. Plus 0.0003. And if you add up all these terms, you start getting the repeating decimal, 0.3 repeating. So if you look at the fact that these terms are decreasing as time goes on, that means we must be multiplying by a ratio that is less than 1. So that's the good news about this. Okay. So what is A1? A1 is 0.3. I'm going to write it as a fraction. I'm going to write it as 3/10. And the second term in here is 3/100, and this is 3/1000. So if I look at these terms, 3/10, 3/100, 3/1000, what is the common ratio that I'm multiplying by? Well, to get from 3/10 to 3/100, didn't the denominator get multiplied by 10? So that would be a ratio, therefore, of 1/10. Since the ratio is less than 1, we know that this series will converge. So let's use our formula. S sub infinity would be A1, which I'm going to write as the fraction, 3/10, over 1 minus R, which is my ratio of 1/10. Okay, clean it up. LCD here is 10. So the 10s cancel up here, 3 over. Bottom is 10 minus 1, which is 9. And 3/9 reduces to 1/3, and lo and behold, isn't 1/3 0.3 repeating? I'm hoping you knew that one. That's a pretty common repeating decimal here. So we can do this for any repeating decimal. Now, this one just repeated for the first two, or the first number was repeating. If there was more than one number in the repeating part of the decimal, we might have to change our thought process just a little bit, but we'll talk about that in class. So a few more infinite geometric series applications coming your way, but I just think this process is so cool. I love it. All right, we'll see you guys